button. Okay, hit record. So again, we're going to talk about dimensional analysis here to start class. We had already done the first problem on this page, so we're going to look at the second problem on using dimensional analysis as a problem-solving tool. The main thing I wanted to show here with this example is that when we're looking at converting pounds of ethanol present in a gallon of ethanol, 1.00 gallons of ethanol, we have a couple conversion factors given. You wouldn't ever have to know non-SI to SI conversion factors, so we wouldn't expect you to memorize the gallon to liter conversion. You would always have that provided to you. The density of ethanol, again, you wouldn't be expected to have this memorized. This would be a given, but what I want to show in this problem is how to use a density like a conversion factor, because we do this a lot in problem solving, and that we can just use a one-step dimensional analysis solution to solve this problem. There are other ways to solve this problem. You could convert the gallon to some sort of mass unit, and then you can plug the mass unit into an equation that relates density. You know, density is mass over volume. So we could always go back to equations, but sometimes it's nicer just to be able to use a density like a conversion factor. So let's see if we can solve for the number of pounds of ethanol present in this quantity in a single kind of line of dimensional analysis calculations. So I like to always start dimensional analysis with what I'm looking for. Sometimes if we forget this step, we can get lost in the problem of what it is we're trying to find. So I'm trying to find the number of pounds of ethanol. And I'm going to start with what I'm given. It's probably pretty obvious that gallon's going to be in the numerator, not the denominator. Worst case scenario of dimensional analysis is you get to the very end and the thing you're looking for is in the denominator. If that ever happens, we just have to flip the entire equation. But we can usually sense when that's going to happen. But we're going to start with what we're given here, a gallon of ethanol. And then I can convert it to liters. So 1 gallon is 3.7854 liters. We should generally never be rounding a result because of the conversion factor. If we think we need to round a result because of our conversion factor, either A, we need to investigate the conversion factor and see if it's an exact conversion. Like, for example, the 2.54 centimeters exactly in an inch. That's an exact conversion. That's not 3 sig figs. Or if we had, let's say, a more precise number of gallons. Let's say we had gallons here to like 6 placeholders. If we had like 1.255234 gallons, I'd have to go look up a more precise gallon to liter conversion. There's more digits known in that conversion factor. I just don't need them for this problem. If you go to the daily quiz area in Carmen, I have a file that has almost every conversion factor to as many digits that are known. And if it's rounded off to like the 13th digit or something. A lot of these values have to be very precise for like shipping purposes. So a lot of these conversion factors are very precisely defined or given. If you need that information, you could always look it up. Okay, so we've gone from gallon to liters. Now I see milliliter here, and so that's what kind of cues me in. I need to convert liters to milliliters. Now that's a conversion that we have to know how to do, but it's not too hard. That 1 liter is 1,000 milliliters. Now this is a conversion factor that we just have to know how to use that metric prefix milli. And if you recall last time we talked about giga, mega, kilo. On the big side, that's 10 to the 9, 10 to the 6, 10 to the 3. And then on the small side, centi, 10 to the minus 2, milli, 10 to the minus 3, micro, 10 to the minus 6, and then nano, 10 to the minus 9. That's kind of the range that we'd expect you to be able to convert without being given those definitions or those conversion factors. Okay, and so then we can go and use the density here as the conversion factor, because what I can write is that the ratio is I have 0.7894 grams per milliliter of ethanol. So if I kind of track so far, I've converted gallons to liters, liters to milliliters. Now I've converted milliliters to the mass of ethanol. If I calculate here, I would be calculating the number of grams in the given quantity of that gallon of ethanol. But of course, we don't want grams. We don't even want kilograms. We want pounds. So I have to do 2 more steps. So I'm just going to zoom out so I get the, because the other conversion factor I need, the kilogram to pound conversion's above, so that would be given to us too. So we're going to use this conversion factor here as well. So I just have to go from grams to kilograms. So of course, 10 to the 3 grams per kilogram. and then the final conversion, 2.2046 pounds per kilogram. So I have 2.2046 pounds per kilogram. And so at this point, I'm just doing the calculation. And so my calculator says the 6.5877 bunch of digits. So it's about 6.59 pounds. Now, why would I round this to 3 placeholders or to 3 significant figures? Well, let's think about sig figs for a minute. One, I'm multiplying here exclusively, so I only have to count sig figs. And so I start with 3 sig figs here. And then if I look at every other conversion, I have more than 3 sig figs here. Again, if I needed more, I'd look up more. This is an exact conversion. There's exactly 1,000 milliliters in a liter. There's not one sig fig there. That's an infinite number of significant figures in that conversion. I have 4 sig figs here. And then here it looks like I have 5, but again, that's actually, most conversion factors, again, are either going to be exact or they're going to be rounded off. This is actually rounded off. And if you're not sure, you can always look up. Rarely do you have to do that on a lecture example. It might be more in the lab that you have to look values up to, a little bit more preciseness. Okay, so I just wanted to kind of hammer on the idea of sig figs is that this is the ordinary kind of measured value in the problem. That should be the one that limits us in the very end. And then the only other thing that might limit us is densities aren't very well known. So densities are usually given to like 3 or 4 placeholders. So like the density could have limited us if we had a much more precise volume. Okay, so 6.59 pounds for that gallon of ethanol. Now let's talk about cubic conversions for a minute. Cubic conversions come up a lot with density. It gives us a relationship between milliliter and a cubic length unit as well. We'll see that a cubic centimeter, you probably know this, but a cubic centimeter is exactly a milliliter. In fact, let's start with that, or kind of define that already, just to make sure that we know this. So that a cubic centimeter is exactly a milliliter. Again, I bet a lot of people knew that coming in, but if you didn't know that, that's an exact conversion. So that's kind of our relationship between the liter and that cubic length scale. And that gets us into thinking about the cubic centimeter is a centimeter by a centimeter by a centimeter. How does that relate to the cubic meter, which is, of course, a meter by a meter by a meter? So cubic meter is relatively large, cubic centimeter relatively small. What would our conversion factor be, or how many cubic centimeters would there be in 1 cubic meter? So if I think about 1 cubic meter, that's equal to 1 meter by 1 meter by 1 meter. And I'm kind of thinking again of like the idea of an exact meter by an exact meter by an exact meter, trying not to get too confused with sig figs here. And so what I might then recognize is that if I want to convert to cubic centimeters, I might think, okay, this is just 100 centimeters now along each length of the box. So 1 meter by 1 meter by 1 meter is a cube would be 100 centimeters by 100 centimeters by 100 centimeters. And so 1 cubic meter would be equal to 100 centimeters, where I cube the entire conversion factor between the 100 centimeters and 1 meter. And so there should be 100 cubed centimeters cubed in 1 cubic meter. Now that conversion is not worth memorizing. It's not worth memorizing that there's 10 to the 3, and that would be, I think that's a million. Let me just, math in front of a big group is always tricky. Yep, that's a million. And so that's 10 to the 6. One silly thing like on a calculator like this is you can always change the scientific notation mode. You can have your calculator just take an answer. If we do 100 caret 3 for 100 to the 3, we can change our mode to scientific on the calculator, and it'll go 1 times 10 to the 6. So if you're ever on a problem, especially on a test, when you see a number and you're like, oh, I need to convert to scientific notation, of course it's not super hard to do that, but on a test, you're like counting decimal places, just switch to scientific notation mode, it'll show you on your calculator. And then you might just want to remember to switch back to floating. That's kind of normal number scheme. And so again, I just like to remind calculator tips and reminders. People come into this class from all different points, and some people haven't done math in a while. So, but to come back to the conversion factor for a minute, when I'm converting a cubic meter, if I'm using this conversion here, what I have to do is I have to cube the conversion factor. So I'm just needing to cube the entire conversion factor between meters and centimeters. So I realize there's 100 centimeters in a meter. The conversion factor has to then go 100 cubed centimeters cubed in 1 cubic meter. And so this would be equal, of course, to 1 cubic meter times 1 meter, 100 cubed centimeters cubed. So I'm cubing the entire conversion factor. So when converting volume units into cubic length unit, we have to cube our conversion factors. And then our conversion factors can be relatively simple and straightforward. You know, like there's easily 100 centimeters in a meter. That's not hard to remember. But what's maybe sometimes challenging to remember if we have to convert cubic meters to cubic centimeters is cubing that conversion factor. So this is a problem here. I'm not going to throw this to you guys in terms of doing this one on the lecture quiz just yet. We'll do a problem later on Carmen. But for this one here, let's just do this problem here together, converting 225 liters to cubic meters. And then one of the things sometimes it gets confusing when you're doing problems at home, it's very easy just to go to like a solver. Like you can go to your phone and just type in 225L equals M caret 3, and it'll tell you on your phone. Be careful when you're doing conversion problems to try to do them the way you have to do them on a test. Let's actually put it this way. No conversion factor is given. That's what I'm trying to say. So convert this quantity here without any conversion factors being provided to you. How would we do this conversion? Well, the way I would be thinking is, I know there's that 1 milliliter and 1 cubic centimeter, and then I know there's 100 centimeters in 1 meter, and I can know that I can cube that as well. And then I would be thinking that there's 1 liter is 1,000 milliliters. So these would be all the conversion factors in my head that I would know and be thinking about how to apply them in the problem. So these would have to be known by you, not given on the test. But this is a relatively straightforward conversion as long as we know and can apply these conversion factors. So the number of cubic meters, I'd write this out. That's what we're looking for, starting with what we're given. And then I would just be kind of thinking, let's go to milliliters. One milliliter is 1 cubic centimeter. And then again, 100 centimeters in 1 meter, cubing that entire conversion factor. And so let me carry out the cubing of every value here. So 1 cubed is 1 still, so 1 cubic meter, again, it's 100 cubed centimeters cubed. So to carry this out, 225 times 1,000 divided by 100 caret 3. And so the result here, that's just showing the conversion factor here, how you put that in the calculator. And so we carry out the math here, we get 0.225 cubic meters. Answer C if we're looking for it here. So cubic conversion's not hard, but we just have to remember to cube the conversion factor. The big step here is just remembering that we're cubing our conversion factor in a problem like this one here. Okay, so let's look at another sig fig question just to kind of wrap chapter 1 up here before we get into chapter 2. And so this problem here is just, again, kind of looking at density. We use densities a lot in the class, so we'll do an example where we're trying to find the density of an object. And you probably have thought or seen an example where if you have some sort of an object, imagine like a cube or a piece of metal or something, you want to know its density, what you might do is work out the mass of the object, put on a balance, figure out its mass, and then our generic example here, the object's mass was 50.00 grams. And then you might take that object and put it into like a container, a volume, where you have the volume kind of recorded here, let's say we're at 75 milliliters, we add our object to the water, and it's going to displace the water upward to 125 milliliters. So you're just kind of putting the object in the water, seeing what the volume changes to for the water. And then by displacement of the water, you can work out the volume of the object. And so for this example here, the beaker went from 75 mils to 125 mils. So the volume of our object would be 125 milliliters minus 75 milliliters. Of course, that's 50 milliliters, but how many sig figs does that number have? What's that?
It's an infinite number because it's an exact number?
Well, not exactly. I mean, so this is, I think, the tricky part of sig figs is trying to understand when we're trying to imply a number is just an ordinary lab measurement. So I think we're trying to portray the 75 to 125 mil changes here as being some sort of like an experiment. And so those are meaning to be like ordinary lab measured values. And so then the lab measurements or values that are appearing to look like lab measurements are subject to sig fig rule. So I'm looking at this is 3 sig figs, this is 2 sig figs, and I'm subtracting them, I need to apply the subtraction rule. And so if we have this 125 minus 75, this is about placeholders, and so 50 here should end up with 2 sig figs. Now, again, sometimes we get confused. Our calculator, if I just do 125 minus 75, my calculator says 50. If we said 50 in a different context, if I said you had 50 milliliters, an object had a volume of 50 milliliters, you'd probably say that's 1 sig fig, and that would be right. If a different context, we just say in a problem you read, an object has a volume of 50 milliliters, you would probably say that's 1 sig fig. But if you said the volume of the object, if I had maybe some sort of thing filled to 125, I withdrew liquid till it was 50, and I knew it was 50 to the nearest one placeholder. Or excuse me, if I went from 125 to 75 and took the difference and got 50, I would then be looking that would be 50 with 2 significant figures. So I would be looking at the placeholders and saying if this was good to the one's value, that's good to the one's value, then the subtraction is going to be good to that same placeholder. So 50 should have 2 sig figs here. And so then when I think about calculating the density of the object, it had 50 grams, 4 sig figs, and then we're dividing that by 50 milliliters with 2 sig figs. And so when I get the density, should have 2 sig figs. So 4 divided by 2. Now I'm counting sig figs. So we count sig figs when we multiply and divide. We round to the lesser value of sig figs. When I add and subtract, I'm looking at the actual placeholders. I'm looking what is the greatest value placeholder each of those values ended in, which value has the higher placeholder. They each have the same, the one's placeholder. So we round that to 50 with 2 sig figs. So both digits here are significant in 50. If we're writing the milliliters, it would be 5.0 times 10 to the 1 milliliters. To be unambiguous to show 2 significant figures on that result. I also like underlining. Decimal places help too. So I'm doing problems by hand. I'll just underline and kind of note the last digit that's significant in the quantity. And let's come back to why this works. If you're sitting there thinking, why are we rounding accordingly? Think about it's all about the plus minus 1. It's all about the last digit in the number carry the uncertainty. There's at least 1 unit of uncertainty of milliliters in each of the 125 and the 75 numbers. When I carry out the difference, the plus minus is about 1 to 2 milliliters. It's that inherent uncertainty in the value. If we were to find that the plus minus was like 10, then we would have rounded it to 1 significant figure on 50. So it's all about the uncertainties. And if that's confusing, then we just got to go to a stats class and actually look at propagating uncertainties. Anybody in a stats class this semester? Have you learned that yet by any chance? Okay, you probably will get there at some point. It might even be next semester, or if you took more stats, you may get there. But it's all about propagating uncertainties. Sig fig rules are a generalization of a more careful or detailed statistical analysis. So how can we get a better value for, like let's say your job was to refine that experiment that we just did to get a more precise density. And let's say you had 2 choices. Should we go use a new balance? Should we go use one of those analytical balances that records to the nearest 0.0001 gram? Because if you notice, the mass is only recorded to 50.00 grams. Should we go use a better balance? Or should we find a better way to measure the volume of the object? I think it's pretty obvious, right? We should use a more careful way of measuring the volume of the liquid before and after we displace the volume with the object. And so why don't I go find a graduated cylinder that has more careful markings on it so I can note the volume to greater precision. So most graduated cylinders are marked with markings about every 1 milliliter, and we should be able to interpolate between the nearest 1 milliliter. And I can even look up and find even more precise, if you have more markings on your graduated cylinder, you can even get to the nearest 0.01 milliliter with a graduated cylinder. So if I just use a more precise tool to measure my volume, instead of a beaker, let's use a graduated cylinder, then we should be able to get a better result. And so the next example, here, let's throw this to you guys just to work out the sig figs on this one. So try to work out the significant figures to calculate the density of the object in this problem. And then the code for today is subatomic. Feel free to compare with your neighbors if you want. Definitely talk here. All right, the results are looking good. I mean, we're almost 100% right on this, that we end up at 3 significant figures here because our difference had 3 significant figures. Now, one thing that I was thinking in this problem, if we had just looked here and said that has 3 sig figs, so the result has to have 3. That's not quite right. We got to be a little careful with that. We actually have to carry out the difference, note the sig figs here, and then use that number of sig figs. Imagine the difference here was like we had one, let's say 52.5 as the first volume, and then our second volume was 104.0 milliliters. Let's say same problem, gives you the same difference. That we'd have to be careful here. Like if we were looking at this being 3 and saying it has to be 3, we might look at this math here and say 4 minus 4 divided into 6 has to be 4, and that wouldn't quite be right, of course, because it would only be 3 still. So we have to make sure to carry out the actual math, note the sig figs on a subtraction step, kind of, one tricky part sometimes is should you round? If this had to be rounded off, should we have rounded or carried out the calculation without rounding yet? That's more of a lab issue. On exam questions, don't let that confuse you. Just think 3 sig figs dividing into 6 sig figs gives you 3 sig figs here. Okay, so we will have a few more significant figure problems spread into the next couple lectures. If you go to the daily quizzes, there's a lot of examples in the first round of daily quizzes. Probably through midterm 1's daily quizzes, you'll see a sig fig problem probably just about every day. Just because there's a lot of nuance here, and it's really just an order of operations problem more than it is anything else, just kind of needing to apply the rules in that order that we do the calculations in. And there's variables that I don't necessarily want to bog down class just yet with, but we'll look at some more examples. Like one key tricky part is what about scientific notation mixed in with sig fig problems? There's a couple examples in the daily quizzes that get into that. We'll probably throw one into lecture that gets into kind of the mixing scientific notation and significant figures. But for now, so we'll kind of get away from chapter 1 by topic, get into chapter 2 here. So hopefully the key topics that we're talking about in chapter 1, some basic chemical terminology in the first couple of sections of the book, classifying matter, but then getting into more of the data analysis, the significant figures, some different units that we're using, and then using dimensional analysis as a tool for, of course, converting units, but also problem solving. So in the chapter 2, we're going to be looking at the sort of how we know about the composition of atoms in the first part of the chapter, getting into atomic structure like proton, neutron, electron counts in the middle part of the chapter, and then towards the end getting into things like atomic weights, a little bit about the periodic table, and then into sort of trying to classify a few different key categories of compounds and trying to learn some systematic nomenclature, some systematic rules for how we name some different categories of compounds. I also like that section to try to introduce us or to even remind us of some different types of categories of compounds that we probably know and have seen already, and then can probably even know how to name a lot of things, and from those names try to sort of understand something about those molecules. Okay, so chapter 2 here, kind of just gave this introduction here, but we're starting with the discovery of atomic structure and modern atomic theory, kind of up front here, getting towards naming at the end of the chapter. Okay, so atomic theory began probably as early as the early 1800s in terms of just like more like a thought experiment that different elements were, or anything that's matter is probably comprised of atoms, and then an atom began to thought of as just like some sort of sphere where each atom would be probably representative of a different type of element. Some elements were known at that time. There's a periodic table, I think in chapter 7 that we'll look at, that'll have kind of a time period for when different elements were discovered. And some of the earliest elements that be discovered were in the sort of 1700s by the alchemists. Alchemists would try to burn things they would find like in earth, like iron ores. They could take an ore that contained iron and oxygen and determine by burning off the oxygen, and they would get to what they determined to be iron. And you could do that with different types of ores and get different types of metals. And what would happen is they would try to break down, it was almost like that scheme from chapter 1 where they're trying to break down the matter into smaller components. And when we get to that smaller component, they would try to break it down any way they could think of, mostly burning or beating the crap out of it with pressure. But through those techniques, they were able to find, okay, we're reaching stopping points where we can't divide anymore. Those became known as the elements. And so the earliest discovered elements were things like iron, zinc, carbon was pretty early on discovered in terms of there being different substances, different properties. These substances had different characteristic properties. And then they started discovering things like reacting units was another thing they started looking at, was when you took these things and reacted them with different sort of other substances, that there were like whole number multiples. And so from the whole number multiples became kind of the idea of sort of coefficients, or subscripts as we now know them in formulas for matter. So Dalton's atomic theory kind of began with a few postulates, and it's kind of interesting to note a few of these postulates aren't entirely correct. But he's also making these postulates well before we even know what elements really are comprised of, what makes them different, and what most of the elements actually are at the time. And so this work, again, mostly a thought experiment, that elements would be comprised of small particles. We call those atoms. The atoms of the same of a same element would be identical to each other. So if you imagine having, determine that you have an iron, like you have the element iron present, that all the atoms in that sample would be identical to each other. Now, you guys probably know that's not entirely correct, because a given element, most elements exist naturally as more than one isotope. And so some elements, if you look very carefully at the different atoms within the element, one could have a slightly different mass than another. We call those isotopes. But the different isotopes tend to have very similar properties. So there's really not much of a different property of isotope A versus isotope B of iron, or the different isotopes of copper. Carbon has key isotopes like carbon-12, carbon-13, and a very small trace of carbon-14. The properties of these atoms aren't greatly different from each other. So when you say all the atoms are identical, they kind of behave identically, might be one of the postulates you're getting from the atomic theory from Dalton. So all atoms are identical to each other. Not entirely true, as we have found since then, but this was the postulate at the time in the early 1800s. One key postulate, and this is an interesting one too, is that elements cannot interconvert to each other through simple chemical reactions. And I believe at the time he had said any reaction, but now we're going to limit that to chemical reactions, thinking that if you have carbon, you're not just going to be able to mix it up in a flask and turn it into nitrogen. Like, it's carbon, it's staying carbon. You're not going to spontaneously find a set of reactions that turn all those atoms into nitrogen. Now, there are physical reactions. You can actually do some really cool physics experiments where you bombard atoms with protons or bombard them with neutrons, and you can actually turn nuclei into other nuclei. This isn't easy. This isn't something you're just going to mix up in a flask like in Celeste Lab. This is something you're going to do under like government watch groups watching you and what you're doing. Like, this isn't easy stuff to do. It's not easy to do physically, and it's not easy to do it like, in terms of the actual like science itself, and some of the risks are high when you do that kind of work. So not easy to do this, but there are physical reactions. I think it's important to note that you can actually interconvert elements, but not easily, and not cheaply, and not legally. Or not mostly legally. So then compounds form when atoms from more than one element combine, and then you get a compound that forms, and the ratio of the atoms or the elements in the compound would be like a whole number. So if we take carbon plus O2 when we form CO2, that we're going to get a ratio of 2 oxygens for every 1 carbon in that formula. So it kind of gave us the idea that the reacting units here of either 1 to 1 in terms of the carbon and the O2 molecule reacting together, O2 being the stable form of oxygen. Interestingly, I doubt they knew this in the 1800s, that O2 was diatomic oxygen. But if you took what we now know as molecular oxygen, combine it with carbon, and you form CO2, that the idea is that you get a 1-to-1 ratio of your reactants, and then the ratio of the oxygen to carbon in the formula is 2 O's to 1 C, and that those are the whole number ratios. Those are more or less exact ratios that you find for every one of those molecules has those ratios intact. Okay, and so this also led to things like the law of conservation of mass, that you're not creating or destroying mass when you do these types of reactions. When you're interconverting elements, you're just exchanging the bonding nature in carbon versus oxygen into CO2. So we're not creating or destroying mass. So mass is not created or destroyed in chemical reactions. So you carry out a chemical reaction, the mass you had before is going to equal the mass after. And the law of multiple proportions is that the reacting units are constant, so that whenever you have a reaction, you get these whole number multiples. I'm not going to write that out, but you just get whole number multiples in reactions when elements are interconverting into compounds. So we'll look more at chemical reactions when we get into chapter 3. So probably early next week, we'll start talking about writing balancing reactions. I'm sure that task itself isn't super challenging. As we get into chapter 3, we'll also talk about formulas and how we get them from data. And after midterm 1, actually, we come toward the end of chapter 3 where we get into stoichiometry. If you remember, that's the topic of quantifying details of chemical reactions. So if you start thinking ahead of really the actual quantification of how many grams of product you get, how much grams of this reactant reacts with that other reactant, those are end of chapter 3 problems we'll see after midterm 1. Okay, so let's get into here a set of experiments that were done to try to elucidate what we now know about atomic theory. And so one of the first experiments done to kind of probe subatomic theory was J.J. Thomson's discovery of the electron in 1897. So at this time, you have to understand, scientists would think that the element is the indivisible form of matter, that once you have a given element of iron, you can't break it down further. Well, not so fast. So J.J. Thomson put a high voltage on an atom. I think it was a copper atom, not exactly sure what he was putting a high voltage on, but a particle was given off from that piece of matter when that really high energy in the form of electricity was hitting the metal. A subatomic particle was given off. Now, how did we know it was subatomic, and how did we know it was a particle? Well, you get this beam that was lighting up a screen, and so you could create a particle that lights up the beam. When you apply the high voltage, take the high voltage away, the particle and that screen lighting up goes away. And then you can also have a magnetic field that could be placed into the beam path of this particle, and that magnetic field would bend the trajectory of the particle, and so we can move the particle around with two things, a magnetic field and an electric field. And so you can move the particle around, and it was going towards the positive direction of an electric field, and so that was telling us that this particle had a negative charge. Now, we now know it was the electron that was being generated in this experiment. At the time, what was known was that this electron had a mass-to-charge ratio that the experiment measured. This isn't worth memorizing, but one of the key details of the experiment was it furnished the charge-to-mass ratio, or if you invert it, the mass-to-charge ratio of this subatomic particle. And so the idea of it being subatomic was that if you had a piece of matter that you couldn't break down further, and here with this high voltage form of energy, you're breaking the atom down, that this had to be some sort of subatomic particle. And this was then quoted as the discovery of the electron. And so then Millikan, about 12 years later, what he tried to do was to try to suspend particles that were created by atomizing like an oil. So you atomize an oil into carbon atoms and different atoms from the oil spray, and then on those droplets of that oil spray, you could then, through a high voltage, in this case using an X-ray, so instead of using high voltage electricity, use another high form of energy known as an X-ray. So using an X-ray source and intersecting these atoms with that X-ray source, that was of high enough energy to cause that subatomic particle to be given off by the atoms in that spray, and then the electrons would just stay attached to the particle droplets. And then because the particle droplets have now a larger mass, you can then apply a field and then try to see how long it kind of takes the particles to drop down and reach the bottom of your sort of instrument. And so what this experiment was able to determine was the mass of the electron and the charge of the electron. And so instead of having a charge to mass ratio, we were now able to then identify the actual mass, the actual charge, to identify that the mass of the electron, 9.11 times 10 to the minus 31 kilograms. Again, not worth memorizing, but a really small amount of mass, and it's about 1/2000th the lightest known element, being hydrogen. So this is clearly a subatomic mass, so definitely a subatomic particle, had been discovered in J.J. Thomson's work. And then we also then get the charge of the electron, negative 1.61 times 10 to the minus 19 coulombs. We could look these numbers up more precisely, but this experiment was determining the mass and charge of the electron was its key discovery, was through what we call the Millikan oil drop experiment. And so Marie Curie was discovering that different elements were naturally radioactive. And so some elements like polonium and radium were discovered to undergo different types of radioactive decay. And so you put the radioactive substance inside of a block, and then you take the sort of particles that are being given off by the radioactive decay, and then 3 key types of decay pathways were observed. One of them was a particle that was moving upward a lot towards the positive direction of the electric field. This was the electron. And so one of the pathways, one of the radioactive pathways that those elements were decaying by was creating an electron. And so that became known as the beta ray. So beta rays are just electrons being given off by matter that's decaying through beta decay pathways. Other pathways led to a positively charged particle because we were seeing that it was heading, she was seeing that it was heading towards a negative direction of an electric field. And so this was telling us that this particle is positively charged. And this turned out to be the helium nucleus. Now this is an interesting question. I've spent maybe a half hour trying to figure out when they knew that this was the helium nucleus, because I don't think they knew it then. But what they knew then was that it was a more massive particle than the electron because it wasn't moving downward very much by the electric field. So if you think of the mass to charge ratio, very little mass, a lot of charge, so the electron's bending big upwards, a lot of mass, just a 2+ charge, but not the charge to mass ratio is not very big, and so the particle is just moving downward a little bit. And so this ends up being the helium nucleus. Now, why the helium nucleus is a key pathway that radioactive substances are giving off in their decay pathways is because this is really the most stable nucleus. So it's a really stable, small nucleus, and our bigger elements are just giving off the helium nucleus as they're decaying to smaller elements. I think uranium's the biggest element that naturally occurs on the surface of Earth. So if you go bigger than uranium element 92, all those elements have already given off helium atoms or other pathways that led to smaller atoms. So our heavier elements beyond uranium, after the Big Bang, presumably probably had been present, and their radioactive pathways, their half-lives were so short that they've already decayed into smaller atoms. So I mentioned before that if you look at if you take a snapshot today of every given element, its natural occurring isotopes, that those are just reflective of where we're at this moment in time relative to the start of the Big Bang, or the creation of all these different nuclei. And so we're just living within that small snapshot of time. But so then there's a third pathway which carried no charge. These were gamma rays. So if you think of X-rays as being a high energy form of radiation, high energy form of light, if you will, gamma rays are even higher energies than X-rays. And so these are like X-rays, greater energy than X-rays. So a really high form of energy being given off by matter. Now, it would have been nice if this was like a neutron or something, but it's not exactly a neutron because you may be thinking here we get the negative electron, we get some particles for the helium nucleus, and then maybe the neutral particle would have been a neutron, but it was actually just a high packet of energy known as a gamma ray, even higher energy than an X-ray. Let's break helium down for a minute, just because we'll get into atomic symbols here in a minute. I'm just thinking here that you guys probably may be looking at the 4 and the 2 and the 2+ and thinking, what are we looking at here? The 2 is the atomic number. This is the number of protons in the nucleus of that atom. So helium's defined as having 2 protons in its nucleus. 4 is the mass number. The mass number is the sum of the neutrons and the protons. So it's the sum of the neutrons and the protons. So if helium has 2 protons and then 4 protons and neutrons, it therefore has 2 neutrons. So that helium nucleus has 2 neutrons, 2 protons, and then this is its charge here. And we'll see, like, this is getting ahead, but I think we know this coming in. I don't think it's too surprising to know or to think the electrons on the outside of the nucleus. So an atom can exchange its electrons. It can lose electrons, it can gain electrons. It's not gaining or losing protons very easily. That nucleus is kind of locked in, like we were saying. So not easily to chemically change that nucleus. But now the electrons spinning around the nucleus, we can kick them off. If we lose 2 electrons off of helium, it now has a 2+ charge. And so helium 0, like an uncharged helium atom, this would contain 2 electrons. The protons and electrons are opposite in charge. So if I have 2+ particles, so 2+ particles, and I have to have 2 negatively charged particles to counterbalance that. So the electron and proton opposite in charge. That's a slide coming up in a couple of moments. but that gives us 2 electrons for an uncharged helium. And if I kick these 2 electrons off and go down to 0, that's 2 plus. So the helium 2 plus has those 2 electrons removed, so therefore bears the net charge of 2 plus from the nuclear charge of 2 positive particles. So in other words, this is just a helium nucleus. So the nucleus of the helium atom without electrons is helium 4, or helium 4-2, with a 2 plus charge. Again, we'll be looking at atomic symbols. I just had written this atomic symbol and thought you guys may have been confused of what it was trying to portray. We'll talk more about symbols as we continue. But there's one more key experiment that kind of furnishes really what we were just talking about, where the electrons are. And so in 1910, you have to remember, scientists didn't know how atoms were sort of putting these protons and electrons within the atom. In fact, the neutron itself hadn't even been discovered, and I'm not even sure the thought of there being a neutral particle is even in their purview yet. The actual discovery of the neutron itself wasn't until 20 years after this experiment, so I'm not entirely sure. It's really like challenging to try to get in the minds of what scientists would have known 100 plus years ago. But if you don't even know there's a neutron, you just know there's probably positive particles that counterbalance the negative particles, the next question is, well, how are they situated? Do we just have all of the positive and negative particles intermixed together? That's this model here. This is called the plum pudding model, or it's just called like a mixture of all the subatomic particles. And that actually was a prevailing model at the time, was that atoms would just have all these different particles intermixed together. So your electrons mixed with your protons. And so then what the scientists did was they took a piece of gold foil, and so really, really thin. So it's like thin as a piece of tissue paper, piece of gold foil. And so why gold? Well, gold has a lot of particles. It has a lot of electrons, a lot of protons. So it has a lot of subatomic particles. And so then, but the thought was that they'd still be like interdispersed. And so then what was fired at those particles was the alpha particle. The alpha particle, if you recall from the previous slide, this is that helium nucleus. So we're going to fire this really high energy, if you think probably fast moving particle, we're going to take this relatively massive particle fired at the sheet of gold and then see what happens. And so if you think about it, it's like you're firing a really high energy particle at a really thin piece. You're probably thinking it's going to go straight through. And so the scientists thought that the particles would just go straight through if this were the prevailing model. So because there'd be nothing in the way. If you think of helium, if you're thinking of this like plum pudding model, there's no buildup of mass. There's not enough mass that would be built up to deflect the alpha particles off of its trajectory. But what was found is that there actually was a lot of scattering. There's even back scattering of particles, meaning there was the fast-moving high-energy particles are bouncing backwards. So imagine you're firing a particle at a piece of tissue paper, and I like this quote here from Ernest Rutherford. It was quite, the most incredible event that has ever occurred to me in my life. It was almost as incredible as if you had fired a 15-inch shell at a piece of tissue paper, and it came back and hit you. So think about that. Think of having a weapon or a mortar, and you fired at a piece of tissue paper, and you have particles being deflected off of that piece of tissue paper. And so that was what then led to a different model, and the prevailing model that since has had other experimental validation through like X-ray diffraction experiments, but that being the accumulation of the mass of the positive particles and then what are now known as the neutrons within the nucleus. And so a gold atom, it's going to have AU, so it's going to have 79 protons, and it's going to have a lot more than that of neutrons packed into a single nucleus. And so you now have a nucleus that has about probably 100 times the mass of that helium particle. So you now have the accumulation of mass that's so high that if that helium particle strikes that nucleus, it's going backwards. And so now it can counter that particle and go backwards. Instead of it being particles that are 1/4 of the size or smaller compared to the helium nucleus, where it would probably go straight through, we now have the accumulation of big massive nuclei, where we strike the nuclei with that helium particle, it's being deflected backwards towards us. Now, there's still not a lot of atoms in the way, so a lot of particles still do go straight through the piece of gold, but we're getting the scattering due to the nuclear model. So this led to the prevailing model of the nucleus, that the nucleus is where the protons and neutrons reside in the atom, and the electrons, being so small, must then be spinning around that nucleus. Now, the electrons themselves, if you start thinking about how the electrons are, I think this makes a lot of sense. You have a light particle, it's probably going to be moving a lot faster than the more massive and smaller proton and neutron. So let's summarize, and then let's look at the relative mass difference between the proton, neutron, and electron, and then make one other observation and kind of move on from this topic here. So Thomson's cathode ray tube experiment, that discovered the electron. The cathode ray tube was actually lighting up the old type of monitor, if you remember the TV screens from like a big monitor. Those are have a fluorescent screen. If the electron hits it, it lights up. And so it's the same type of technology used in the old style TVs. So that was used to determine the mass to charge ratio of the electron and the discovery of the electron itself. Millikan's oil drop experiment furnished the calculation and the discovery of the charge and the mass of the electron. Curie's radioactivity experiments, for which she paid her life. She died of cancer I think she was in her 30s, but she did get 2 Nobel Prizes for her work. But her work discovered the alpha, beta, and gamma decay pathways of matter. The alpha particle was used in Rutherford's work, and then that was used in Rutherford's experiments to discover the nuclear model of the atom. And then I think it's interesting to note the proton itself discovered 1919, and then the neutron not till 1932. So much later, the neutron's discovered, and along the way, I think they were picking up isotopes. The different elements had different masses, et cetera. So the nuclear model of the atom, the nucleus contains our protons and neutrons. The volume occupied by electrons, the electrons are occupying most of the space of the atom, very small amount of space being occupied by those massive particles. And if you think about it, the massive particles are just getting out of the way of those electrons. So they're just getting out of the way of the electrons so that they can spin, if you will, around the atom. We'll talk about different types of orbitals that the electrons and how we can understand where the electrons are around an atom, or some information about where they might be around the atom when we get to chapter 6. But most of this, the atom is empty space. It's not being used at any given moment of an atom, but it's not being used for good reason, because there's lots of positive electron repulsion, or there's negative positive attractive force between the electrons and the nucleus. But if you think of one atom versus another, the electrons repel each other. So the empty space we see around atoms is due to that electron repulsion. So atoms are generally small. You're talking 1 to 5 angstrom. So small we invented a unit to portray their small size. 1 to 5 angstrom is 1 times 10 to the minus 10 to 5 times 10 to the minus 10 meters. Because 1 angstrom is 1 times 10 to the minus 10 meters. So 1 times 10 to the minus 10 meters is an angstrom. So angstrom, really small amount of space. So you're talking about atoms 1 to 5 times 10 to the minus 10 meters in diameter. And so then the protons and neutrons later discovered, as we mentioned on the previous slide. And let's end with this page here for today, which kind of notes the relative masses in the atomic mass unit scale. We'll talk a little bit later about how you can convert AMUs to something more reasonable like grams. But the proton carries a mass of about 1.0073 AMU. The neutron, 1.0087 AMU. So they're approximately equal to 1 atomic mass unit. And then the electron is much smaller. It's about 5 times 10 to the minus 4 AMUs. So the electron very, very light compared to the proton and the neutron. So the protons and neutrons reside in the nucleus. The number of protons defines the element. So hydrogen being the smallest. So hydrogen's 1, helium's 2, etc. And electrons and protons have identical but opposite charges. So the charge of the proton is the opposite of the charge of the electron. And so this helps us just understand proton-electron balance. If we were to look at carbon, for example, carbon's element number 6, a neutral carbon atom should have 6 protons and then therefore 6 electrons. So for neutral in charge, usually we don't write a 0 to imply neutral. If I see carbon, no charge indicated, I'm assuming that's uncharged. And so that would mean carbon has 6 electrons to balance out the 6 protons. And then our atomic symbols, like we were talking earlier, kind of tell us the atomic symbol as a subscript. The mass number is a superscript. The most abundant isotope of carbon is carbon 12. So that's carbon 12, so that would be 6 protons, 6 neutrons. And then carbon has different isotopes. Isotopes are where we change the neutral particle. So if we have carbon 13, that's 7 neutrons. But the proton count remains the same. We're not changing, if we change a proton count, we change the element anyways, but carbon 13 still has 6 protons, therefore picks up an extra neutron. Carbon 14, even another neutron on top of that. Okay, so we'll pick up from here onto the next slide into whatever day of the week it is, Friday. So have a great day, everybody.